Aluminum and tin. Aluminum extraction. Aluminum is less electropositive than the alkali and alkaline earth metals. In nature, aluminum does not occur in its free state. In the combined form, it is the third most abundant element. The important minerals of aluminum are bauxite, corundum, diaspore, feldspar, kaolin or china clay, mica, cryolite, aluminite or alum stone. Aluminum is extracted from bauxite, which is Al2O3 with 2 waters, hydrated with 2 waters. When bauxite has iron oxide present in it, it is known as red bauxite, and when it has silica present, it is known as white bauxite. Bayer's method is used to purify red bauxite. The red bauxite is dried and pulverized. It is then heated with concentrated sodium hydroxide solution, 50%, under pressure at 423 Kelvin. Aluminum oxide is converted to soluble sodium meta-aluminate, while iron oxide and silicate impurities will remain undissolved and filtered off. The diluted filtrate is digested with freshly prepared aluminum hydroxide and agitated at 290 to 325 Kelvin. Sodium meta-aluminate is hydrolyzed to insoluble aluminum hydroxide and is removed by filtration. The aluminum hydroxide is then ignited at 1473 Kelvin. This forms pure alumina, Al2O3, according to the reactions below. So the first step is under pressure at 423 Kelvin. Then we get this aluminum hydroxide at temperature between 290 to 325 Kelvin, which we filter off, and then heated and ignited at 1473 Kelvin results in the production of pure alumina, Al2O3. Using Hall's method, red bauxite is powdered and fused with sodium carbonate. Alumina, Al2O3, is dissolved, forming sodium meta-aluminate, and iron oxide will remain unaffected and filtered off. The fused mass is treated with water. Carbon dioxide is then passed through the solution at 325 to 355 Kelvin to get the aluminum hydroxide precipitated, which you can see represented in this second step here. The aluminum hydroxide is then ignited at 1473 Kelvin to pure alumina, Al2O3, according to these reactions below. Serpek's method is used in the purification of white bauxite. The white bauxite is powdered and heated to 2075 Kelvin with coke in a current of nitrogen where aluminum nitride is formed. You can see that here. Silica is reduced to silicon and volatilizes off according to the reactions below. So here's the silicon. The aluminum nitride formed reacts with water to form aluminum hydroxide, which you can see right here, which is ignited at 1473 Kelvin and will yield pure alumina, Al2O3, in the second reaction shown. The Hall and Heroult method uses electrolysis of the fused alumina. Pure alumina is dissolved in a fused mixture of cryolite with a small amount of fluorspar. The solution is electrolyzed in a big ion box. The box has a lining of carbon which acts as the cathode. The anode consists of a number of carbon rods suspended vertically in the molten electrolyte. The electrolyte is kept fused and maintained at 1173 to 1273 Kelvin. Added cryolite will decrease the melting point from 2273 to 1173 Kelvin and increases the electrical conductivity. Aluminum is formed at the bottom and the cathode is drawn out periodically. Oxygen is liberated at the carbon rod's anode. These rods are slowly burnt off and should be replaced from time to time. All right, so here is an image of the electrolysis of fused alumina, Al2O3. We have our graphite cathode and our graphite anode. And in this molten cryolite solution is our purified aluminum ore, our Al2O3. At the cathode, what's happening is pure solid aluminum is building up, and at the anode we are getting oxygen, O2. So here's these carbon rods forming the anode that periodically have to be burned off to react with this oxygen. Properties of aluminum. Aluminum is a soft, light silvery metal with a melting point 933 Kelvin. It is malleable and ductile and a good conductor of heat and electricity. The first ionization energy of aluminum is low, whereas the second and third ionization energies are relatively high. It has a common oxidation state of +3, resulting from the 3 valence electrons from the outer shell. Aluminum is quite reactive and forms a layer of oxide coating on the surface when exposed to air. That layer prevents further oxidation of the aluminum metal. Uses of aluminum. Because aluminum is resistant to corrosion, it is used in making cooking utensils and picture frames. It is used for making electrical transmission cables. In an aluminothermic process, it is used for the production of metals like chromium and manganese. In the form of foil, it is used for wrapping various food items, household, and consumer products. A mixture of ammonium nitrate and aluminum nitrate is used in bomb making. Aluminum powder is used in flashlight bulbs for indoor photography. Mixed with linseed oil, it is used in silvery paints. It is used as an insulating material and as a mirror in reflecting telescopes. Tin extraction. Cassiterite, SnO2, is the ore used in tin extraction. Cassiterite contains a very small amount of tin, 10%, with the rest being silicate, iron, tungsten, manganese, and copper impurities. The ore is concentrated through the following process. The ore is crushed and powdered. The silicate impurities are removed by gravity separation. Tungstates, iron, and manganese are removed by magnetic separation since they produce magnetic properties. The concentrated ore is then roasted in a large rotary furnace. Sulfur and arsenic are removed as volatile oxides, while copper and iron sulfides are converted to the corresponding sulfates and oxides according to the list of reactions below. The roasted ore is next cooled and washed with water to dissolve all the sulfates. Iron oxide and other light matter is washed away. Since the tin stone is heavy, it collects at the bottom. At this point, the stone is now 60 to 70% concentrated and is called black tin. The black tin needs to be smelted. Black tin is mixed with powdered coke or anthracite along with small amounts of limestone. The mixture is smelted in a reverberatory furnace. The charge is heated to 1500 Kelvin. Tin oxide is reduced by the carbon to form the free metal, while impurities, if any, are removed as slag, fused silicates. The reduction of tin and the formation of the fused silicates occur according to the reactions below. The black tin is then put through a purification process. The main impurities in the black tin obtained are iron, sulfur, arsenic, and tungsten. The following processes are employed in refining the material: liquation, poling, electrorefining. In liquation, black tin is melted on the sloping hearth of the reverberatory furnace. Due to its low melting point at 505 Kelvin, tin melts earlier before the impurities and flows down the slope while impurities are left behind. Sulfur and arsenic burn off, forming the volatile oxides, and escape. Poling. The molten metal is then stirred with logs of green wood. Any tin oxide will be reduced to metal. Iron and copper form oxides with the help of atmospheric oxygen and form a scum on the surface, which is removed. The tin is 99% pure when this method is used. Electrorefining. Impure metal blocks are suspended in an electrolytic cell containing tin sulfate, dilute sulfuric acid, and hydrofluorosilicic acid. The sheets of pure tin act as the cathode. Upon passing current, pure tin will get deposited on the cathode. Properties of tin. Tin is a silvery soft metal. It is ductile and malleable. Its melting point is 505 Kelvin, and the boiling point is 2,960 Kelvin. Oxygen does not react with tin at room temperature, but forms tin-4 oxide, SnO2, when heated in air at 1,800 Kelvin, according to the reaction here. Tin has no reaction with water at room temperature. Tin will react with dilute hydrochloric acid according to the reaction Sn plus 2HCl to produce tin 2 chloride and hydrogen gas. Tin will react with concentrated HNO3 nitric acid, forming metastannic acid according to this reaction below, the reaction of tin with HNO3 to produce this metastannic acid. With concentrated sulfuric acid, as shown here, tin forms its sulfate, and tin reacts with chlorine to form tin-4 chloride, shown by this reaction. Tin reacts with sulfur to form tin-4 sulfide, shown in this reaction. Tin reacts with oxygen to form both divalent and tetravalent compounds. In a mildly acidic solution, hydrogen sulfide forms a brown precipitate with tin-2 ions and light yellow precipitate with tin-4 ions, shown by these two reactions. Tin-4 sulfide, SNS2, is soluble in basic medium and in the presence of excess sulfide ions. Oxides of tin. Tin-4 oxide, or stannic oxide, SnO2. This oxide exists naturally and can be found in the ore cassiterite. It can also be obtained by heating the element in oxygen or by treating with concentrated nitric acid and subsequent ignition of the metastannic acid, according to the reactions shown below. So we have heating the element in oxygen to form SnO2, or treating the element with concentrated nitric acid, then taking that intermediate, igniting it, and getting the tin-4 oxide product. Tin-4 oxide is a white solid and is amphoteric. Tin-2 oxide, stannous oxide, SNO. This oxide is obtained by heating tin-2 oxalate, as shown here. The presence of carbon monoxide prevents the oxidation of tin 2 oxide to tin 4 oxide. Tin 2 oxide is a black solid and also amphoteric in nature. Uses of tin. Tin is widely used in plating iron to resist corrosion. Tin foils are used for food containers. It is used in tin amalgam for making mirrors. It is used in making alloys such as bronze, bell metal solder, white metal, pewter, and gunmetal. Tin 4 oxide is used as a polishing powder known as putty powder. It is also used in glass and pottery manufacture and making white enamels.